All right, let's look at particle motion as it relates to antiderivatives. If you're looking for information on derivatives with particle motion and how derivatives can be used to solve problems, you need to find another lesson. And if you want to print the guided notes sheet that I give my students, there is a bit.ly link that will allow you to print the sheet. Very quick refresher on the relationship between position, velocity, and acceleration. Velocity is the derivative of position. Acceleration is the derivative of velocity, or the second derivative of position. And we'll be camping out on that first line. We'll be talking about the relationship between velocity and position here. And we're going to talk about displacement versus total distance. And the displacement of something that is moving is the net change in position on that interval, which means you find where you finished and where you started, and you find the distance between those 2 points. So if you have the position function already, then it's really easy, because displacement, you just find the position at those 2 times and you subtract them. If that is a negative answer, then that means your displacement is you moved to the left. Your net change was a movement left. If it is a positive answer, that means you moved to the right. It tells you how many units you move in whichever direction. If you're given the velocity and you want displacement, well, we need to work back to position, so we will find the antiderivative of velocity and evaluate that on the interval a to b. And the antiderivative of velocity is position, and then when you evaluate that definite integral, you end up doing the exact same thing we did up here. Final position minus initial position. And again, the sign of that answer will tell you whether you moved that many units to the left or to the right. Total distance is different, though. For total distance, what we can do is we can find the sum of all of the distance traveled, and I doubled down on the word traveled here. The sum of all of the distance that we traveled between each of the resting times on that interval. And one thing to remember is resting times, an object is at rest when the velocity is equal to 0. Okay? And so there are 2 ways we can work on and get total distance. This thing's not working. There it goes. One way is to find all of the times objects at rest. And again, I'll reiterate, the object is at rest when the velocity is equal to 0. And once you have all of those times, we'll find the displacement between those times, or on all of the intervals created by the resting times. So for example, if we find out that the velocity is equal to 0 at 2 and 5, then the total distance from 0 to 10, well, we go from 0 to 2, we take a break, we go from 2 to 5, we take a break, then we go from 5 to 10. We need to find the displacements on all of those intervals. And so it would be x2 minus x0, x of 0, and then we add to that the distance traveled from 5 to 2, and then we add to that the distance traveled between 5 and 10. And notice in this one I did use absolute values because I am interested in the total distance that we have traveled. So if I travel left, then the displacement will be a negative value. We want to make sure that we're adding up all the positives. So this is the way that we did total distance when all we knew was the derivative approach to doing this. We'd find the derivative of position, set that equal to 0, get those resting times, and then compute all of the displacements. However, if you're given the velocity and not the position, sometimes it is easier to find total distance by doing the definite integral of the absolute value of velocity. And let's think about why that works. If I take the absolute value of velocity, the times when velocity is positive, we're moving to the right, is unaffected. However, if the velocity is negative and you're moving left, well, those absolute value signs will make that velocity positive on those intervals. So we're always traveling in the same direction, which means this interval would end up giving you the total distance traveled. And sometimes this is the easier route. Sometimes it's easier to go with the first example. If it is a calculator active question, so if you have a calculator, and I'm thinking in the world of AP calculus because some college classes won't let you use calculators, but if you have a calculator active question that can do definite integrals, and your velocity is an explicit function, meaning you can actually graph and look at the graph of the velocity function, then this is definitely easier to do the absolute value in a calculator. Otherwise, we kind of have to analyze the problem and decide what would be the better option, whether we should use the absolute values antiderivative or if we should do the displacement between resting times. So I have a few examples I want to look at. Move my head out of the way. There we go. All right, and the first 2 are calculator active. And so we have a particle moving along the x-axis. This is the velocity of that particle. It says the initial position at time equals 0 is x equals 0.085. So I'm going to make a note to myself that my position at time 0 is 0.085. Let's see, what is there's the question. What is the displacement of the particle from 0 to 5? Displacement is strictly, and because I'm given the velocity function, I'm going to have to do the antiderivative of the velocity function, which is the arctan of t squared plus t minus 1. And then we'll measure that from 0 to 5. And because this is a calculator active question, I'm simply going to type that in the calculator, then I'll write down the answer. Turns out the initial position was not needed. Not needed in order to answer the displacement. So I'm going to go to my calculator now, and I'm using the TI Inspire, and the hot button for the definite integral is Shift plus, and it was 0 to 5 of the inverse tangent of t squared plus t minus 1. So t squared plus t, let's do it this way, plus t minus 1 dt. And always, when you're using calculators, always double and triple check that you do indeed punch everything in correctly. Inverse tangent t squared plus t minus 1. All that looks great. All that looks wonderful. And also make sure you're in radian mode, because if you're in degree mode, this one will give you a wrong answer. I'm going to hit Control Enter to force the decimal, and I'm getting 5.5035. Let's keep green. 5.5035. That is a positive value. That means that on this interval, we traveled 5.5 units to the right. Let's look at the next one. So we have another particle moving along the x-axis. Again, it's a calculator active question. What is the total distance traveled? Total distance. Total distance means I need to, and we're given velocity, I need to find the antiderivative of the magnitude of velocity. My little squiggle s's are stupid today. That's better. And I'm not going to write the function. I'm just going to write v of t dt. And we need to evaluate that from 0 to 3 pi. And I'll just throw this in the this is a calculator question, so make it easy on yourself. So I'm going to go to my calculator, Shift plus. I need to go from 0 to 3 pi of the absolute value, and on the TI Inspires, the absolute value that I use is right next to the 9. Click that. And I need to type in the function sine cubed of x. Isn't that what it was? Yes. So it's sine, and on the Inspires, the way you do that is you have to do sine of x and close that, then to the third power. That would be good enough. If you want to put the whole thing in parentheses, because it may confirm that you are indeed cubing the sine and not the argument of x, you can do that. This is with respect to x, Control Enter, and oh, well, that's sexy, isn't it? 4. The answer was 4. And yeah, I did. So on these calculators, it doesn't matter if you use x's or t's. I noticed that I did sine x dx. It doesn't really matter. It'll give you the same answer whether you use x's or t's or any other variable. So there's 1 and 2. Now let's look at this one, because we have velocity this time presented as a graph, and it says we have a slug crawling along a vertical wire. The position of the slug in inches above ground is given by, this says x equals, and which is fine. There's nothing wrong with calling it x, but I think since we're traveling vertically, I'm going to change that to y. I'm going to change that to y, since we're moving vertically. The velocity of the slug measured in inches per minute is represented by the graph to the right. What is the displacement of the slug on the interval 0 to 10? So displacement, we do not use absolute values. So displacement is going to be the integral from 0 to 10 of v of t. And now we need to figure out how we're going to work that out. And we just have to remember that definite integrals are a reference to area. And this graph creates a bunch of nice little geometric shapes to represent the areas between this graph and the x-axis. I'm going to pause the recording for a minute while I work out those areas, and then we will talk about how we'll use them to get our answer to part A. Okay, so here are my areas, and you can see my arithmetic over here. I used a trapezoid for the interval from 3 to 8. the height of the trapezoid being 4, and the bases are 5 and 2. So we have areas of 6, 14, and 2. But we have to remember that for this problem, for displacement, if I'm below the x-axis, we actually need to subtract that area of 14. So we have 6, and then we went down 14 units, and then we went up 2 units, which gives me a final answer of -6. Is that right? Yes. That gives me a final answer of -6, which means the displacement, this slug on this interval, went down 6 units. So if you want to, or 6 inches. So you could say that the slug moved down 6 inches in these 10 minutes. Good. Then for B, what is the total distance traveled? Well, that's different than displacement. Total distance would be 0 to 10 of the absolute value or the magnitude of velocity. And so this time we will use only the positive values, because that negative part of the velocity down here, when I take the absolute value, that's going to basically take this negative part of velocity and it's going to move up and look like this. And so here is the graph of the absolute value of velocity. The 6 and the 2 were unaffected, but when I flipped that up, that 14 is now a positive 14 plus 2, which gives me a total distance of 22 inches traveled. Cool. And then part C. At times t equals 0, the slug is 10 inches above ground level. How many inches above ground level is the slug at 4 minutes? Oh man, it's at 4. I thought it was going to be 10. Okay, so I have an initial position. The position, and I'm going to again change this to a y because we're moving vertically. My position at time 0, so we're starting at the 10-inch mark. And the question is, what is the position at time 4? And this is your net change theorem. I need to know what is the displacement. I need to know how far did this slug move from 0 to 4. So I need the displacement from 0 to 4. And if I started at 10, I'll just add the displacement to my initial position. And so y of 4 is going to be that initial position plus the displacement would be 0 to 4 of velocity dt. Initial position is 10. And now we need to compute area again over here. I don't need the 14. I already know 0 to 3 is 6. So 0 to 3 is 6. And then I need to subtract this area from 3 to 4. And that area is half of 1 times 4, which is 16 minus 2 is 14. And so we are 14 inches above ground. Cool. All right, and then there's one more example I wanted to look at. One more example, and this is a non-calculator question. And it says we have a object moving along the x-axis. I've given you velocity, and I want the total distance traveled. And so there are a couple of ways we can do this one. When I see total distance, my initial thought is always, I need to find the antiderivative of the magnitude of velocity. And my velocity this time is t squared minus 3t. And since it's a non-calculator question, I'm going to go ahead and write that equation, that function for velocity. And then we have to wonder, how in the world can I do that without a calculator? And if I'm dealing with absolute values and I don't have a calculator, my go-to approach is to think graphically. And so I'm going to sketch a very rough graph of this function. And so I'm going to do that by setting this equal to 0. And you will find out that this velocity equals 0 at t equals 0 and 3. And so graphically, my velocity looks like this. We cross the t-axis at 0. We cross the t-axis again at 3. And my velocity is doing this. Comes down. It's a parabola that opens up. I have the two roots. Wow, I just missed it. Let's move that up some. There we go. So there's my velocity graph, but we're supposed to be doing the absolute value of velocity. So my velocity is the blue graph, the absolute value of velocity. I'm going to do that in red. Absolute values will not affect things that are already positive. So these pieces above the x-axis or the t-axis won't be affected. This piece below the x-axis will be reflected up and over. Good. And so I need to figure out what that section would be, and then I need to figure out the section from 0 to from 3 to 5, because we're measuring total distance all the way up to 5, and graphically I need these two areas. I need this area and I need this area. So I will split this up. I'm going to split this up from 0 to 3, and then I'm going to add to that an antiderivative from 3 to 5. And the 3 to 5 portion of my velocity function was unaffected. So I can go ahead and put t squared minus 3t for my velocity from 3 to 5, because the absolute value did not affect it. However, absolute value does change the sign of my velocity from 0 to 3, so I'm simply going to multiply the velocity by a negative. That is the transformation that flips a graph over the x-axis, or in this case, the t-axis. And we have two definite integrals to compute, and these are fairly nice antiderivatives. They're just power rules, and so we'll find the antiderivatives of both of these, and then we'll add their values to get the total distance traveled, and I'm going to pause the recording and do that really quick. Hey, here's my final answer. It's really ugly. I'm not going to go through the hassle of cleaning that up, but I did want to show you how, if you do not have a calculator and you need to worry about that absolute value component, this is how you could go about solving this if you want to work at it on this from the absolute value perspective. And in just a second, I'm going to show you how you could do this through the other method, because I did say that one of the ways we could get total distance is you could find all the times objects at rest and then compute the displacement on each of those intervals. So I'm going to work that out really quick and show you what that would look like, but I'm going to work it out while the video's paused, because I'm already getting close to 20 minutes and I don't like having long videos like this. Okay, so here's most of the setup for this approach. You find the resting times. When your object is at rest is when your velocity is 0. We already had that. We knew it was 0 and 3. Then we need to find the displacement on each of the intervals. So we're going to go from 0 to 3 and then from 3 to 5. And to do that, we would need to find the antiderivative. So this approach really isn't that much different, because I still need to find the antiderivative. And technically there is some unknown constant for the antiderivative. However, in problems like these, when you subtract or when you find the displacement, that constant is not going to matter. It's going to end up subtracting away. So we don't need that. And you'll see that if you plugged in 3 and 0 and 5 and 3 to this, subtracted them, took their absolute values, you're going to end up doing the exact same thing we ended up having in number 4, the first way I did number 4. So the amount of work is about the same. It's just a slightly different thought process as you approach it. And so I am done. That is it for this lesson. Goodbye.